Okay, so here's what you're going to need. We've gone through electron configurations. You're going to need a blank periodic table. You should have gotten one. You're also going to need 4 different colors of colored pencils. If you did not get any of those things, then you need to find out where they are. The colored pencil should be in cabinet 154. So we're going to start off with the blank periodic table. If you're going through this and I go too fast, you can pause it or stop it or restart it or whatever you want to do. And you can go back and look at it as many times as you want to. So we're going to look at how the electron configurations work along with the periodic table. And the way that it's set up is exactly the way the electron configurations actually work for each of the elements. Okay? So across the top of the periodic table, you've got 18 groups, right? So we have 18 of those columns we call groups. We also have 7 of the periods going across. Remember the 2 there at the bottom here are going to be for the period 6 and 7. So let's start back up here at hydrogen. Right? We know that hydrogen has 1 electron. Its 1 electron goes in the lowest energy level, which is 1s. So its configuration is 1s1. If we go across to helium, helium has 2 electrons. So we're going to write in helium's box its configuration, which is 1s2. If you go down to the second period and you get to lithium, right? Lithium is the 3rd element. It's got 3 electrons. It would be a 1s2, and then it would be a 2s1. So we don't have room to write all of the configuration, so we're just going to write the end of the configuration in each case. So for lithium, we're going to write 2s1. And then we know beryllium has got 4 electrons. It's a 1s2, 2s2, so we're going to write 2s2 in the box. You can kind of see where this is going to start to go. Now we go over to the other side of the periodic table. We get to boron, right? We know that boron has 5 electrons. So it's got a 1s2, got a 2s2, and it's got a 2p1. So we're going to fill in 2p1 for boron. And we're going to do the same thing for carbon, which is, of course, a 2p2. And then we go to nitrogen and oxygen and fluorine and neon. And we get all the way to 2p6. And we know that the second energy level is now filled, right? And that's why neon is a noble gas. Okay, the neon and helium and everything else that's going to be in group 18 are the noble gases. They don't want to react with anything because they have a completely filled outer shell, right? Their highest energy level is completely filled, and that's really stable. So according to what we've done so far, the first energy level, right, is just the 1s. The second energy level is the 2s and the 2p. So the right side of this periodic table here is exactly 6 elements wide because the second energy level has a 2p that can fit 6 electrons. Now, the rest of the third period should be pretty simple. It should look like the second period. So we have a 3s1, a 3s2, and then we have all of the 3p's, all the way out to 3p6. So as you're going, you should be filling these in on your blank periodic table so that you have a version of this that you can follow along with and you can study. When we get to the 4th period, when we get to the 4th energy level, we know that after 3p comes 4s, right? According to the Aufbau principle, right, we said the order of the energy levels is a little different when we start talking about orbitals. So the 4s comes after 3p, but then after 4s is 3d. And of course, right here in the middle of the periodic table, there is a spot suddenly for 10 elements, because the 3d and the 4d and the 5d and the 6d, they can all hold 10 electrons. So in the 4th energy level here, we're going to fill in 3d1, right? And we got 3d2, we have 3d3, and before you start filling in the rest, pause for a second and think about what we had talked about. We talked about there are exceptions to this rule, where there are some electron configurations that are more stable when they half or fully fill their D and F, right? This is something that we had just talked about. So instead of writing 3D4 for the next one, we're going to write 4S1 3D5. I know we got to stuff it in there a little bit because it's a lot to write in one little box. But it does that because, remember, a 3D4 would rather be a 3D5 because 3D5 is half filled. It's more stable. So it goes and it borrows from the 4S2, and it creates a 3D5 situation, but now it's one less in its 4S. And then we go into the actual 3D5 that didn't have to borrow, and 3D6, and 3D7, and 3D8. And then again, you have to pause and think. 3D9 is not going to exist because it's only one electron away from being 3D10, which is fully filled and a lot more stable. So a 3D9 is actually going to borrow from the 4S. It's going to become 4S1 3D10. And then we have the actual 3D10 that didn't have to borrow. It was already 3D10. And then we have the rest of the 4Ps, just like we had from before. And this pattern is going to continue, right, through all of the fifth period. So now we have 5S1, 5S2. We have all of the 4Ds, including the exceptions. And we have all of the 5Ps. When we get to the sixth period, the only difference now is we eventually are going to branch off down here and we're going to get to some Fs. So after 5P, we get to 6S, so we have 6S1, 6S2. And then we start to get into the 5Ds, but again, remember, we have this break here in which we have to go down here, and we have an area down here that is exactly 14 of these elements across, because an F can hold 14 total electrons. So let's go down and fill those in first. After 6S comes 4F. So we have 4F1, 4F2, 4F3, 4F4, 4F5. And then again, pause, remember, 4F6 is only one away from being a 4F7. So it wants to go and borrow from the S before it. So it would be a 6S1 4F7. And we have the actual 4F7 that didn't have to borrow. And then we have 4F8, 4F9, 4F10. And then 4F13, once again, is going to borrow because it's a one away from being 4F14, which is completely filled and stable. So it's going to go and it's going to get the 6S and borrow from that. So you have 6S1, 4F14. And you have the actual 4F14. Now, after 4F, we learned we go back and we have 5Ds. And now we go back up here, and under the 4Ds, now we have the 5Ds. So we can fill in the 5Ds, and then we can fill in the 6Ps. And this pattern continues all the way through to the end. So the seventh period is going to look just like the sixth period, except that all of the energy levels are going to be bumped up one. So now we have the 7S's, we have the 5Fs, we have the 6Ds, and we have the 7Ps, all the way out to element 118, which is where 7P6 would be. We don't have to go any further than that because obviously there's no more elements than that. So this pattern that you see here is a really simple pattern that you need to start to be able to visualize on a regular old periodic table. We're drawing this out as a study tool, but this isn't necessarily something that you're going to have with you at all times. You're not going to be able to use this on the test or, on the test. You can use it on a notes quiz, but you can't use it on the test. So you need to start to get familiar with what this pattern is. And again, it's a pretty simple pattern. In fact, we can see on here that all of the S's are all located here in group 1 and group 2. Right? Group 1 is all S1. Group 2 is all S2. And they follow the period numbers. Period number 1 is energy level number 1. Why are there only 7 energy levels? Because there's only 7 periods on the periodic table, right? They match up perfectly. So this whole area over here where all the S's are the S block, right? We can color that in. So that whole area there on the left is the S block. You can go ahead and color it if you want to pause and color it in before you go on, you can, or you can go in and color it later, right? The second area that we're going to look at is over here on the right. We can see all of the 2P's are together over here. Okay? So we have 2P, 3P, 4P, 5P, 6P. We have all of the P's together in one block, and so we're going to call that the P block. Right? The P block can be colored. Don't color in helium. Right? Helium is kind of different. It doesn't fit exactly. Even though it is a noble gas, it does not fit with the other P, so we don't color it in at all. So that's our P block. We then, here in the middle, have all of our D's together, and so that's our D block. And then finally, here at the bottom, we have all of the F's together, and so we remember that as the F block. And so this right here is going to be really useful for us. Again, it's not something that you're going to be able to be staring at all the time when you're taking a test or in future times. I want you to get this down in your head that this is what the periodic table is telling us. So when you're looking at a regular old periodic table, you can see this. And then we're going to be able to use this to be able to do electron configurations much, much faster than we were doing before. Because now, as long as we know what the location of the element is on the periodic table, we can figure out the configuration really, really quickly. Let me give you an example. And I'm just going to write this on here, but you do not have to write on your blank periodic table. Next slide. So once again, if we looked at neon, we know that neon is 1s2, 2s2, 2p6. Sodium is the next element after neon in the periodic table. It's the first element in the third period, so it would be 1s2, 2s2, 2p6, 3s1. The only difference between these two elements is that sodium has an extra 3s1. So we could just simply write this as sodium is neon with a 3s1. That's just what we call its core notation. It's just a super abbreviated way of writing out an electron configuration. It's a lot easier. So to do a core notation, you have to write the symbol of the noble gas that comes before that element, not after. It has to be the one that comes before it in brackets. And then you're going to write the rest of the configuration as usual. Okay. So let's do just a couple more examples of this so we get used to it. And then you can finish up your electron configuration homework packet that you have where you have to also write core notations, and you can fill those in. So here's a periodic table just so we can see a regular one in front of us while we do this. Okay. So let's go back to our chlorine example. Now, for our chlorine example, we are not looking at our colored periodic table right now. We're just looking at a regular periodic table. We know chlorine is right here. Chlorine is in group 17, which is the fifth one over in the P block, and it's in period 3. Therefore, it must be a 3p5. The noble gas that comes before chlorine is neon. So I'm going to write neon in brackets, and then I'm going to write what comes after neon. Okay, so chlorine is essentially just neon with a 3s2, 3p5, right? So I just write 3s2, 3p5, okay? So that's how we're going to go ahead and do these. There's a neater version of it. All right, so let's try another one. Let's do this with strontium. Now, I want you to find out where strontium is. Figure out what the noble gas before strontium is. Write that noble gas in brackets. And then I want you to write what comes after that noble gas. So here's the answer. And you see how we got that, right? Before strontium is krypton. That's the noble gas that comes before it. So I write krypton in brackets. And then after krypton is the fifth period, 5s2. And then we're at strontium, we're done. So we can do this for any of these, okay? So any element can work, and it shortens up things and makes it a lot faster to do. Let's do one more. Let's try silver. So again, I want you to find silver. Then I want you to find the noble gas that comes before it. Okay, so you're going to have to go all the way to the noble gas that comes before it. Write that in brackets. And then from that noble gas, I want you to start counting out what we have. So obviously the noble gas is krypton, right? So krypton, and then we go over here and we're like, okay, so this is the fifth period, so this would be 5s2. And then we start counting out the 4Ds. Remember, these are the